Hi there. Welcome. Thanks for joining. This is a presentation video in brief of Chapter 1 content designed for meteorology students at Floyd Central High School, a dual credit course for Science 111 college transfer credit. The intention of this is to stay connected to the course content, to maybe catch a student up that was absent, or maybe meet a more visual or auditory learner where they might need to see things more than one time. So we will go over some of the same concepts, but for the most part, these concepts will be similar but brief and directly connected to the same thing that we talk about in class. This will also allow us to flip our classroom. So what we will use in class is time to complete labs, activities, build models, to have reinforcing discussions. And the intention here is to allow students to focus on content outside of class time so they can watch these brief presentations, take notes on them, take screenshots, download them, whatever they need to do to make a greater connection to content. And then we can conserve our face-to-face time for practice. And that'll enrich in our learning environment and continue to elevate performance in the course, and most importantly, understanding of our natural and physical world. So why study meteorology? Well, that's a good question. What we talked about in class are the things that allow us to study meteorology. The weather in the United States varies vastly. It influences our daily lives, and it's becoming a point where it's extremely emerging to a safety perspective, especially from the standpoints of our extremes. So we don't have the luxury of controlling the weather. Not yet. Don't know if we ever will, but we will have the ability to hopefully predict weather to help keep players outside during summer football camps or cross-country runners during training camps to stay more safe. And that's what meteorology is in effect of. We're also doing a pretty good job of telling people whether or not they need umbrellas on certain days. And of course, it's always nice to get that snow day, even though we got to make it up. The 2-hour delay is also a wild favorite as well. So when we look at those things, it's good to have a bit of a sport within the science. But most importantly, what we're after is safety. We want to keep more people in the nation and hopefully globally safer through a greater understanding of the fluid dynamics in the atmosphere. So let's look at a few key components here. When we look at the atmosphere in general, we're going to compare it with 3 other things that sometimes get confused, especially at the beginning of a course like this. When we study meteorology, it is a study of an interaction of weather and a certain geography, which is often why geography and meteorology are taught in similar schools at the university level, or they're taught in similar departments. Climate is an average of weather over time. So think of a climate being something that is an average over maybe a human's lifetime. About a century of data is brought into play to get an average conditions list of weather. Weather is the day to day or hour to hour, or in some cases, minute to minute changes. Some of you can remember in the winter season arriving to school and it might be 50 degrees, very warm, and by the time you leave, it might be 30. Conversely, it may flip-flop. So we have experienced those changes from time to time. So meteorology is a study of a blend of all of those. We'll study the fluid dynamics and the flow of water in the atmosphere. The air, we'll look at tendencies of gases and pressures, and we'll try to figure out how they flow, why they behave the way they do, and what laws are present within each one of those systems. So we're able to have a connection to physics, but we're able to appreciate a study through meteorology, which makes it a good connection to a wide range of science and non-science majors at the undergraduate level. Plus, you get dual credit for taking it. One of the diagrams in your book looks similar to this. This is a pretty common weather map. This weather map shows a contoured temperature profile of the United States. And it's very traditional. You can easily see how the colors show us temperature. The darker purples are the cooler temperatures, and then we get into the reds, which are the traditional temperatures associated with warm. We have our fronts that move through, we'll talk about later, but we do have this publicly posted in National Weather Service. Not exactly like this, but we use it a lot. The USA Today posts something like this, and then many of your phones or your mobile applications have charts and tables and graphs and maps that are related to weather as well. So we're more connected today to weather than we ever have been, even though we're not quite as an agricultural of society. We almost keep track of weather more today for simple convenience and knowledge of what to wear. What should we do with the baseball game? Will we be able to have the football game start on time? Will it be too warm? Will snow keep us out of school? So it's more of a convenience and a certain degree of sport that's involved in there. Now, on the safety side of things, meteorology certainly has some safety concerns. The greatest safety concerns is this list. So make sure as you close out chapter 1, you understand that the safety concerns with meteorology deal with lightning, thunderstorms, hurricanes, cold waves, tornadoes, blizzards, heat waves, and fog. So these are definitely geographically connected. For example, Floyd Central High School will not be hit directly by a hurricane, but we may have certain spin-offs of that hurricane. You can probably remember Ike, Hurricane Ike, the remnants of that coming down, creating that great windstorm when we lost power. Some of you were without power for the better part of 2 weeks. Very inconvenient, very odd from just a windstorm. We had peak gusts of 72 miles per hour at Floyd Central during that event. Heat waves and cold waves are extreme. We're certainly remembering cold waves as we battle a winter season. Not quite as cold as the 2014 winter season yet, but we're having our degrees of cool bouts as that polar front changes its location. Heat waves are on the other side of the season. Blizzards don't happen too often. When we do have blizzards in the southern part of Indiana, it's not been uncommon that we have a state of emergency declared, mainly because of the reduction of visibility and the inability of keeping roads passable. Fog doesn't affect us too often. We do have fog limitations, and you can see that, but many of you don't drive through terribly thick fog. Lightning, thunderstorms, we certainly have those. So this is our assault list, if you will, of the hazards that come from meteorology. Another part of meteorology deals with the form of charts and graphs. Excuse me. Charts and graphs are undeniably present in this science. So one of the things we can look at here is this. Read through each one of these carefully. Notice how it's the same thing. We have a temperature, but it's the same temperature, a daily temperature, a record daily low, a record daily high, average daily low, average daily high. So sometimes at first glance, it can be a bit redundant when you consider that this graph is temperature based, but it's not the same temperature. It's daily high, an average high. So we need to have a critical eye when we look at the overall data that comes out with our graphs and charts within meteorology. It is certainly a data-rich environment. Let's jump into the spheres of meteorology a little bit. But before we do, we need to recognize the scientific methods. No class in science will disregard the scientific method. So do make sure you can connect to this traditional method. Even though it's not a recipe, we do solve things that are problem-based all the time. You can't get around it. Those of you that are dealing with technology on a daily basis, which is most of us, constantly have to try to figure out new ways to solve different problems. In technology, we may call them a workaround. You're a problem solver. That's what you're doing. When you go out to your car, if you're driving and it doesn't start, you're going to find a way to figure out how to start that car, whether that's calling somebody, seeking advice, seeking jumper cables. We have to be good problem solvers. And there are certain methods that we use traditionally, but there doesn't have to be a certain recipe. So we can see those. Now let's move into our spheres. When we see Earth spheres, excuse me, one of the things we should understand is spheres are large and small processes. They're not spheres in the sense of a circle. They are spheres in the sense of a system. For example, if I were an astronaut on the moon in subset A, I look back to the Earth and I see a pale blue dot. If I'm closer to the Earth, or I have a different perspective with a different set of lens, I see letter B. Letter B provides much more detail. I not only see the globe feature of the Earth, but I also see the swirling nature of the atmosphere. So I know there's gases hovering above that world. I know the world is blue, especially ours, because of its nature of water, how it has a sphere of water around it, but it also has these land masses. So we have so many spheres. Just as we look at this picture, we have a sphere of the Earth in whole, we have a sphere of gas around the Earth, and then we have a sphere of water upon the Earth. So spheres are things that are a part of meteorology that we can't get away from. The traditional spheres are these five: geosphere, atmosphere, hydrosphere, and biosphere. Sometimes a textbook will throw in cryosphere. Cryosphere relates to the frozen water sphere of the Earth. This textbook doesn't focus on that. Soil is an interface with all spheres. That is the one thread that is interwoven between all, because that is how we can have nutrient value from the ground, even though we don't have to eat dirt, thankfully. But the plants that absorb that, the carbohydrates that are produced, the vitamins and minerals, we see that interface present through soil. So soil is definitely a part and a matrix of the spheres, and it's kind of in its own derivative. So we would study soil science in an entirely different set because of that interaction. The four that we will focus on the most in this course is the geosphere, atmosphere, hydrosphere, and biosphere. Most importantly, the one we will focus on is the atmosphere and hydrosphere. Those two interact significantly. So let's look at the atmosphere. In this slide, you can see a brief composite of what we worked on in lab. If you can remember the layers of the atmosphere and how you built that model of the Earth's atmosphere and those kilometer ranges, the layer of the atmosphere is the one that you're living in is called the troposphere. Look how thin it is. In the composite view, you can see how much of a tiny thin layer that we're living in. You and I have to have that gas. We have to have that presence of troposphere, that right pressure, that correct temperature. And we get to see those things that are out there. The types of clouds that are present in this picture are very, very high level clouds, very almost unusual clouds. Most people wouldn't notice them. And we see how high those are. So some of the clouds that you see on a daily basis are in the troposphere. Some of the clouds that you see may not be a part of the troposphere. They may be very high level clouds. And later in the course, we will study those differences. So let's look at the Earth sphere and see how that sphere can interact with other systems. Specifically, let's look at the hydrosphere. This slide focuses on the hydrosphere, and it shows how there can be multiple subsystems within a sphere. So while the hydrosphere is the Earth's water, we just don't have one simple system of Earth's water. We have the frozen water and massive chunks of ice that you can see that we often refer to as glacial ice. We have groundwater that's underneath our feet that come out in aquifers, that come out in springs, artesian springs. We have surface water. And then, of course, we have surface water that isn't the same because some of the surface water is fresh, but the majority of surface water is salty. So we have a salt water system within the Earth sphere. We have a fresh water system at the surface within the Earth sphere. So even though these spheres seem holistic, they have subsystems which someone that studies the Earth's water, maybe a hydrologist, would go into greater detail of. So it can be quite encompassing when we look at those. But what about the atmosphere? What is the atmosphere made of? Do you remember the three dominant gases in the atmosphere? You should be able to recall and discuss those, as well as being able to tell where they're from. This slide will refresh your memory. Hopefully you can recall from our discussions in class that nitrogen is the most dominant gas in each breath that you take in. We've got about 78% nitrogen, 21% oxygen. Might be a bit counterintuitive that we breathe less oxygen than we do nitrogen, but hopefully we'll understand why in a few slides when we discuss the sources of those. Argon is the leading tertiary gas, the third most dominant gas. And when we look at argon values compared to carbon dioxide, it's quite different. So this next slide reinforces something that I really want to emphasize. This is a hurdle for many in the course or in an understanding of atmospheric science. Carbon dioxide does not make up much of our atmosphere. This 0.04, if we round it to 0.04, is a pale comparison to the 0.93%, 0.93, almost 1% argon. And if we look at that compared to CO2, CO2 is only 0.04. So a drastic difference when we look at that. But carbon dioxide gets so much more press, mainly because it falls into a group of gases, compounds that are able to absorb energy, and they're referred to as greenhouse gases. Argon is a nice stable gas. We use that in industrial applications where we put it in between panes of windows, and the stability allows us to have a greater insulation capacity. So we do see those being used, and we'll explore some of that in a later component of the course. Moving on to the next slide. The system of air that supports our life is constantly being changed in the form of checks and balances. We have the common photosynthesis being a process that allows oxygen to be produced. We have biomasses that are breaking down, and that decay and that decomposition of biomass, that those decomposers on a planet help us release nitrogen in the atmosphere. We elect to burn fossil fuels, and that burns compounds, changes things, and it makes sulfur oxides and carbon dioxides in our atmosphere that we have to watch. We have CO2 that becomes dissolved in seawater. So it's absolutely fabulous that we have carbon dioxide being naturally sequestered in our seawater, but it also makes it challenging to determine what is the true effect of our human activity in releasing CO2. And it makes that a little bit more challenging. And that's part of the reason why you hear about CO2 so much. So the atmosphere is constantly ebbing, constantly tiding, constantly changing as we go through certain things. And as our planet changes, as sea levels rise, as they fall, as our planet naturally warms and cools, as we deforest for paper products, for building products, as we excavate, as we surface mine, we're changing this system. And those are things that, as we understand and have a greater appreciation of a scientific background, then we can understand what is the full extent, or what is a more full extent, of our human activity. This slide communicates a very important greenhouse gas that is so often misunderstood. Water vapor is a significant greenhouse gas on the planet. It helps you and I stay warm, and it changes the most. It ranges, as the slide shows, between 0% and 4%. Where do you think it would be at 4%? And where do you think it'd be 0%? If you consider that the greatest amount of direct sunlight on this planet is near the tropical or equatorial region, then that would relate to the higher percentage. So 4% would be more of a tropical range of geography. That means the 0% must be closer to the poles. Clouds and precipitation would be associated with a higher percent by volume range, which is why it's so often that we hear of clouds and precipitation on a daily basis being produced near the equator. When we have these vapors that are able to leave, and these solids that are able to leave the surface of the earth because of wind activity, then we move into aerosols. Aerosols are tiny particles. They could be solids, they could be liquids, things that don't hurt us when we breathe things in necessarily. If they're called pollutants, then we have a health concern. But most of the time, aerosols are small solid or liquid particles that you and I are breathing right now. Maybe something like dust or dander, maybe something like dead skin cells, maybe something like sawdust that we breathe in that doesn't necessarily cause us concern for health in small quantities. But when we have other compounds, maybe something from the burning of coal, maybe something from the incomplete combustion of a natural gas, then we move into a pollutant. And the pollutant is something that we have to watch carefully because it can damage our respiration system. It can damage our respiratory tract. It could damage our alveoli in our lungs, and it can cause problems within our system. So aerosols are something that we do track. And most air quality management systems at the state and federal level will monitor a certain aerosol suspension of very particular pollutants. And we will talk about those later in the course. So let's look at ozone next. Ozone goes into this layer that hopefully you can recall from our discussion called the stratosphere. That's the layer above the layer that you're in right now, which is the troposphere. And the ozone helps us filter and absorb UV radiation. So it's extremely important. It's very well understood that the ozone layer is compromised. And that's because of the use of things called CFCs. CFCs stand for chlorofluorocarbons. Big word, typically easy to remember. And if you can remember and connect CFC with breaking down ozone, then we're at the level of understanding that we need to. Now, moving forward, there is some interaction within chlorine that's released and within some other compounds that's released that we'll talk about later in the course. But within chapter 1, if you can understand and make a connection to CFCs breaking down ozone, and CFCs are being used in propellants, like in aerosols. This would be used to get paints out of a can or hairspray out of a can, and refrigerants, things that change states of matter easily, so we could transfer energy in and out of systems. That is where we use CFCs and have used CFCs. Think car refrigerants, if you want to remember something in maybe your distant past. Some of you may be even driving a car that still use CFC-based refrigerants. So not necessarily all, most modern cars today are non-CFC. So we do see that depletion that's being met. The next graph here shows the ozone hole. The ozone hole does change, and one of the things we see is it is hopefully going to get better. It's going to take some time. It's a slow process. The reason why it's such a slow process is because a small amount of CFC or chlorine can do a major amount of ozone disruption. So imagine one simple molecule destroying thousands of good compounds. And that's kind of what we get into with this destruction level. So there's been a lot of damage done. Hopefully, if our understanding is correct, we will have an improvement of that. It's just going to take time. So we do see this improvement, this setback, this improvement, this setback, and we see how we are hopefully going to improve the extension here. But can you interpret this chart? Let's see, make sure we can. In the month of November, what we have here is the extent of the ozone hole, and we have it at about 12, maybe 13 million square kilometers. Well, how was it in the same month, which would be November, in the year 2006? Well, in 2006, we had a larger opening. So that leads us to believe that our policy, which is the Montreal Protocol policy, a lot of it set forth in 1987, is working. And if that's the case, then we should be having an improvement. But we can certainly see our introduction of CFCs in this chart. Ozone depletion will certainly cause a greater effect of UV radiation. So I think this is fairly common to most of you, but make sure we can connect to UV radiation and skin cancer. It affects our immunity. We do not want overly aggressive doses of UV. It will cause us to have a compromise. And then it can promote cataracts, which is a big reason why you are not only advised to wear sunglasses during the heat of the day, which would be like your 11 to 3 or just about any time you're outside on a sunny day. Not only should you wear sunglasses, but you need a cap with a bill. Think baseball players. And that's going to help shade that area and keep that UV from scarring that retinal, those areas of your cataracts. So kind of a long-term effect. And when you're young, you don't think about it, but later in life, many of you have had family members or pets, and you've seen that damage, that hazing in their eyes because that's cataract scarring. That's UV damage. Montreal Protocol mentioned before, this was a United Nations effort, one of the most globally effective. Everybody was on board pretty much to get this in effect, and that was put in motion 1987. 190 nations, which was fabulous, ratified the treaty, and it helped to create controls on ozone depleting chemicals. So 2 slides ago, we saw the improvement that was apparent, and hopefully this policy is what's doing that. Unfortunately, we're not having the same effect with current environmental policies, and we'll discuss those ramifications a little bit later in the course. The vertical structure of the atmosphere, we're going to pick up where we left off with our lab. So you've got the layers of the atmosphere, you know ionosphere, you know troposphere, troposphere, you know tropopause, you know those layers. Well, let's talk about pressure. We'll do a couple demonstrations in class, if we haven't already, about the pressure in the atmosphere. But notice this red line. While you looked at the red line in a different chart for temperature working on your lab, this red line now correlates to pressure. The red line here is focusing on a decrease in pressure with an increase in altitude. So if you go to the top of Mount Everest, it's almost impossible to breathe. You're going to have supplemental oxygen with you. Most of the time, we're going to have a very difficult time breathing somewhere around 3.5 miles in the atmosphere. Kind of a short leash. Once we get a little bit below 3.5 miles, the labor that we would have to put into breathing would be so uncomfortable that we would probably stop our ascension. So in reality, we live on a very short leash as far as an atmospheric ascension and pressure perspective. But look at what happens to the atmospheric pressure. It continues to decrease. It's not like temperature. Remember, temperature had a systematic zigzag approach. It got colder in one atmosphere, it got warmer in one atmosphere, so on and so forth. But pressure will always get less as we ascend through the atmosphere, no matter which layer that we're in. And the reason why is because of the effect of gravity. The gaseous material cannot be held together nearly as tightly as lower layers compared to upper layers because of a diminishing effect of gravity. So as we move farther away from the center of the Earth, gravitational forces is allowing gases to flow more freely, spread out, and we have less atmospheric pressure. So that's where we get into problems with the ability to put dissolved gases that we need into our blood system. We have to watch that. Some of you have noticed the effect of that decreased pressure, and you've read things like maybe on the back of a pizza box that you're getting ready to prepare pizza with, and it says heat this pizza at this temperature for this long, and then it gives a sidebar of high altitude instructions. Same thing with home heating. If you heat with certain types of natural gas or certain types of heaters in your house, you have a different setting or threshold for high altitude, and that's because of things that we'll talk about with gas laws and the introduction of temperature and pressure correlations. So here's 2 important statements. An increase in altitude decreases pressure. Increasing altitude causes a decreased temperature in the troposphere. But if we were to move on into the stratosphere does not have a decrease in temperature. And we'll talk more about that in just a bit. 2 odd layers of the atmosphere. They're not formal layers. They're more of a mixture level. We have the homosphere and the heterosphere. The homosphere is a lower layer where the proportion of component gases, being nitrogen, oxygen, and argon, is about the same proportion, helping us be able to breathe at certain levels in the atmosphere, which is nice for pilots. So they can fly small craft, large craft, and they can compress atmosphere from outside, not take supplemental oxygen when they fly at maybe 20,000 feet, maybe 10,000 feet, and they can compress that and we can still breathe easily because of the homosphere. The heterosphere, though, once we ascend past 80 kilometers, this is going to start to isolate gas in shells. We have a nitrogen shell. The outermost shell is hydrogen because of that escape velocity discussion that we had in class. The hydrogen gas has a molecular weight that is less than helium, that is less than oxygen. Therefore, it has the ability to ascend to a much higher shell because of diminished effects of gravity. It's lighter, and so it's able to ascend higher. So do make sure you can understand the difference between a homosphere and a heterosphere. Homosphere is like homogeneous, it's well mixed. Heterosphere is poorly mixed. This would be like having a layer of oil on water. Those of you that we talked about in class that eat natural peanut butter, you open that up, and before it's constituted, you see an oil of peanut oil on the top, a layer of peanut oil on the top, and then you have peanuts, the pulp in the middle of it. The ionosphere is a unique layer as well. Some of you struggled with where to put this in your graph, in your chart, in your model, in the lab that we worked on in class, and rightfully so. Look at the range, 80 to 400 kilometers. Where exactly do you put that? So right now, at this point in the course, if we could just understand what the ionosphere is, how it deals with an electrified layer with an ionized layer of the atmosphere, and how it has a wide range, that's the level that we need to get to. This is also the area where we would see auroras. And auroras are represented by this glowing fashion at the upper part of this chart. Most of you are familiar with those. Some of you that are out of the astronomy course should be more familiar with that content than others. If you didn't have the astronomy, you may want to read about that and discuss in component discussion about how the auroras form from the standpoint of magnetic interaction and the solar wind from the sun. But that's where we would see that. So that 80 to 400. So we start here at 80 and we go all the way up to 400 kilometers, and that's where we have the ionosphere. We've used the ionosphere historically to bounce communications off of, especially communications like that of the radio signals. So as we get close to closing out here, we've got a handful of additional slides. The troposphere, stratosphere. Notice here we do not have a linear temperature change. It's not like pressure. Temperature decreases with altitude in the troposphere. We do have a lapse rate of 6.5 Celsius per kilometer. It is variable, meaning that it changes depending on what time of day it is, where it's at, what it's over. We will work with those and have some sample problems as we transition from chapter 1 to chapter 2. And we will really work with that when we get into the Earth's heating. Stratosphere, notice here we have an increase in temperature. So it's often hard for people to understand that as we ascend, as we move up through the atmosphere, not all atmospheric layers will get cold. That just reinforces the fact that hardly anybody on the planet gets out of the troposphere. Almost all of us are bound to the troposphere. We have a group of pilots that are able to go up into the stratosphere that we could easily isolate in a very small city. And then we even have a smaller group on the planet that we call astronauts that we could put in a fairly small building. And that would isolate those that have gone up that high. But most of us live in the troposphere. It's easy to breathe. When we get to areas and we go to a professional venue, maybe like Mile High Stadium, maybe we vacation in Colorado, maybe you go and take a trip to the top of the Rocky Mountains, and you notice that it's harder to breathe and you can feel your ears pop. And so we don't necessarily like those changes. So most of us elect to be bound by the leash of the troposphere. Mesosphere, we have one of the cooler layers. We have a marked decrease with altitude. Thermosphere, and one of the warmer layers there. There are 3 layers that define ion density there, layer D, E, and F. We won't go into a great detail there. That's more of an electric connection to ionization there in the magnetic field. So if you could just put together that the thermosphere and ionization occurs there, that would be wonderful. And to close out here, we have a brief slide on auroras. We have 2 types that we talked about, and this is redundant to the astronomy course. We have the aurora borealis in the north hemisphere. We have the aurora australis in the southern hemisphere, and they do occur in the ionosphere. Basically, it's an interaction with the solar wind, streaming ions from the sun, highly energetic. It interacts with our magnetic field, and our magnetic field on this planet is drawn into areas that are similar to, not identical, but similar to our geographic north and south pole. And as that interaction happens, we can see a glow in the atmosphere. Most of the time, we need to be up around the Arctic Circle, around 60 degrees north or south. Every so often, we get a very aggressive bout of solar wind that strikes the planet. And if it's during the right season and we're tilted in the right fashion, we in Indiana can sometimes see that. So some of you can maybe remember last year and the year before, there were some events that you could see if you look toward the east during certain times of a 24-hour period to be able to see that. They're very light here. the best that I can remember seeing here caused a light flickering in the night sky. It would be easily dismissed, but it was a formal auroral event, and by far that has been the best over a time period of about 100 years in Indiana. It is a magnetic field effect, and it does emit light. So those are the things that we have in chapter 1. So in brief, as a quick review over chapter 1, this allows us to stay connected to practice and discussions and cultivations of greater lines of thought in class. And you can have your traditional feed for content here. You can take your time, use the program to download or access and repeat. And if you have any questions over anything that I've said and you want to print off the PowerPoint that's available through the webpage, I encourage you to do that, and that'll help you prepare for your quiz and test. Our first quiz will be coming up, and this will be an important tool to use for that. I will give you a study guide in the physical sense and more traditional sense in class. Hopefully you pick that up, and you'll be working on those, and that'll be good guidance. So look forward to talking to you in class, and keep up the good work.